Okay, so today we will start. Oh, how can I get to go to the wrong thing? I need to hold on. Okay, I need to get this pen. Okay, so what today we will discuss is a new unit. It's about clustering, and this is unsupervised. So not like the previously that we learned. Okay, so it's regarding unsupervised learning. So let's see. So unsupervised learning. So over here, it's to find the hidden structures in data. Okay, and for the supervised, the target, we always have label that, or we have like the regression, we have the value. But over here, we don't know the answer. Okay, so that's the hidden structure. So we need to find out the commentaries. So over here, the clustering can be used to do this kind of unsupervised learning. So the idea of clustering is, so based on the word, is it? So the concept is kind of, we can guessing, is it's to try to find some nature grouping in data. Okay, so that items in the same cluster are more similar to each other than those from different clusters. So that's the major concept. So you may have data, is it distributed, something like this. But because we don't have label, like this is group 1, group 2, groups, we don't have the label. So you just have the data. So you just have the data distributed like this, is it? But there is no labeling. Then over here, the concept for clustering is, then we find out, okay, this will be in one group, this will be in another group, and this will be in the third group. So we can group, and they share some common attributes so that we can group them together. So in this case, then later on, then we can say, okay, there are 3 classes. Okay, but how can we group them together, etc.? So there are different approaches. So over here, so generally speaking, this unit we will learn 3 approaches. The very first one is we are going to find the centroid. So we said find centers of similarity using the k-means. Okay, k-means. This is different from KNN. Okay, KNN is k nearest neighbor. Okay, this is k-means. Okay, so the means regarding the centers, and there are number of, and we can specify k number of. But up front, you don't know. Like in this case, you say, okay, I want the k to be 5. Then that's not too close, is it? Basically, it's 3. So if you can find this k number 3, then we can group the data into 3 different groups. So this is the first approach that we are going to discuss. The second one we are going to discuss is to build some hierarchical clustering tree. Okay, so that's the second. And we are going to use some approach we call bottom-up approach. Okay, and the third one is to identify because the shape, it may not be always like sphere shape for a group. Okay, it may be arbitrary shape. Okay, arbitrary shape. And then we use some specified method. It's called density-based clustering. So it's based on the density. Okay, and even like this kind of, you see, this is, so this group are all densely distributed. Is that if you consider like this two together, and then this part is not that densely, is it? So the third approach is based on the density. So we call it density-based clustering. Okay, so this is just some general idea, okay, about the clustering. And we have three different approaches that we are going to discuss. And this kind of clustering, we also call it prototype-based clustering. Okay, so the prototype-based clustering, it just means that each cluster then is going to be represented by some prototype. This prototype is that it can either be centroid, like KNN, is it the means of some similar points with continuous features, is it? Or it can be medoid. So medoid is the most representative or most frequently occurring point in the case of, is that categorical features. Okay, previously we also learned that categorical features. Okay, so that's about a prototype clustering. So the first one we are going to see is the k-means algorithm. Okay, so k-means is that it's good at identifying cluster with a spherical shape, but its drawback, it has some drawback, is because for the clustering, the idea is we have no idea about the group, is it? But for this approach to work is you need to specify the number of clusters up front, is it? So prior. So that's kind of the drawback, okay. So that's k-means. Then let's take a look at how k-means works, okay. So k-means is you render, because that's the name come from k, okay. So you need to upfront pick the number of the centroids. So suppose you pick a k centroids from all of the sample points. Okay, and they will serve as the initial cluster centers. So the idea is like previously, what we draw is that so you have different group of data, and we don't know, is it? It's just you randomly. Maybe you pick this point as a centroid and pick this as a centroid, and maybe pick then this as some centroid. You have three initial centroids. Okay, so over here it's k is 3, is it? Then for each of the sample, so then here is a sample, is it? And here is a sample, here is sample. So for a sample, so this sample, then you don't know how close it is to this centroid, to this centroid, or to this centroid. Is it? You don't know. So you need to find the distance among all the three centroids. Then you find the minimum one. Okay, the minimum one, then it belongs to this centroid. So okay, so you put these two together. Then the same thing for each of the sample, you're going to do the same thing. Okay, and after you kind of group a certain number, all of the samples are assigned, then you also need to update your centroid. Then we need to update the centroid to the central, because initially you pick the centroid for this one, is it? But After you have all of them, you may find the centroid may coming close to this one. Is it? So you're going to repeat this two steps a number of times so that finally, like your centroid is stabilized. Okay, so the cluster assignment do not change. Or we can define some user-defined tolerance or maximum number of iterations. This is kind of similar as what all of the previous learning examples did, is that for the iteration. Okay, so that's the idea of k-means. Okay, then it involves calculation of the distance. Previously, we also learned that regarding the distance. So here the distance for k-means is we can use squared Euclidean distance, okay, between 2 points. But be careful, okay, this 2 points not 2 dimensions, m-dimensional. Okay, but it doesn't matter, is it? So mathematics, you can write like this, is it? So this is square Euclidean. This is vector format in math, is it? And this is the scalar data, is it? So project the sample, is it, into the m dimension. Okay, m dimension, then you square and add them together. Okay, so this is from math, so not too hard to understand, is it? So this is regarding Euclidean distance. Okay, as we can describe the k-means algorithm as some simple optimization problem, basically. So the idea is using iterative approach to minimize the within cluster sum of the square of error. Okay, so here it's within cluster sum of the square of error. Okay, so that's, and we already saw we use this concept quite often, is that that's in the past, it also involved like some kind of cost function, objective function. It's all revolved around the sum of the squared of error, but also within cluster or between clusters, the inter and inter. Previous, we also discussed kind of this concept. And in k-means, this sum of squared of error, okay, and also at some weights, it is also called cluster inertial, okay, because later on we will also see this can be used to pick the optimal number of clusters. Because when you don't know how many clusters we should have, then you just needed to do try out. Is it to try with 2, try with 3, try with 5? Is it to then find the optimal one? And how can you pick? Then we can use this inertia, okay, as some cutoff value, okay. So this is regarding distance calculation in k-means. So for k-means, classical k-means, the initial, be careful, okay, initial centroid, they are not the final one, okay, if you recall that algorithm, okay, the final one, because each iteration, your centroid is going to be updated, okay. But for the initial one, anyway, for k-means, it's use a random seed to place, okay. But with random seed, it also has some downside sometimes. Sometimes it may involve the bad clustering, okay, and sometimes it involves slow convergence, Okay, so that's the downside. And then how can we solve this dilemma? Is it to address this issue? As one approach is you run it multiple times, and each time you pick a different set of initial centroids, is it? And then you find the best performance model. Okay, so that's one approach. You try with different set of random seed. Another one, we call it k-mean plus plus. Okay, k-mean is plus plus. So this is intuitive if you think about this. What they pick the initial centroid is, the initial centroid, they won't pick the close one. They pick further away from each other one. Okay, so the idea is, because with random pick, when you pick the initial centroid, you may say, okay, I pick the initial centroid, I pick initial centroid, then you pick this initial centroid. That's not, clearly you can see this is not a good choice with random, is it? But with k plus plus, then what we can pick is, maybe let me choose this one. Then maybe what it says is further away point. So maybe this one's further away, this one's further away, this one's further away. Is it the three further away from? Then because they are further, so they have a high chance not going to be in the same cluster. So that's the idea. Then definitely this will help much more. Okay. So this is the k plus plus. Okay. For sklearn, it provides a k-means. Okay, k-means. And k-means plus plus is also the default one for k-means. So later on, we will also say, okay, in our examples. Okay, then let's see. So for k-means, how it works. So the major difference is the initial centroids. Okay, initial centroids, the pick. Okay, so it's not randomly seeded. Okay, so over here it says the initialization. This is just regarding initialization. How we do it is you start with an empty set. Okay, and that will be used to store the centroids. And of course, the first one, you don't have choice. You can only just randomly select the first one. Okay, and add it to the set. Is it? And then for each of the sample, it says, if it's not, then you find the minimum square distance. Is it to the centroid? Okay, and then you need to randomly select the next one. Is it? So over here, it's use some weighted distribution. Okay, so based on the Euclidean distance. Okay, so square distance we already see. Is it? And then we just repeat this for a number of times. Then you can find the further away one as the initial centroid. Okay. So this is k plus plus. So the concept is not too hard to understand. Okay. And there is another concept here is that hard clustering versus soft clustering. So hard clustering, so previously what we just discussed, no matter it's random or randomly pick or k plus plus, is it? Then it says for hard clustering, it's each sample in the data set, then it's assigned to exactly just one cluster. It won't be assigned it won't be kind of ambiguous, is it? It's just one, the specific one. For soft clustering, so basically, soft clustering is use a concept of fuzzy logic. Okay, it's use a fuzzy concept. Okay, so fuzzy concept, it's not just 0 or 1. Okay, not white or black. Okay, it kind of can be some in gray area, is it? So that's concept of fuzzy. Okay, so over here, soft clustering is we use fuzzy concept. So a sample can be assigned to one or more clustering. So that's kind of contradictory, you may say, is it? When we say clustering, basically it should be in one or in the other. It shouldn't be in two, is it? But here, what you have to consider is a possibility. Possibility, is it? If you recall previously, we also learned, is it? We also use the possibility concept, as if you recall, basically previously what we learned, like logistic regression, is also based on a possibility, is it? Not 100%. Be positive or be negative. It is just some possibility, is it, with probability. Okay, the probability. Okay, that's the concept of fuzzy here. Okay, so soft clustering is use the fuzzy concept. Okay, with what? So it's not replace 100%. It's certain probability for the sample point belong to a cluster. Okay, so that's the idea called fuzzy. So anyway, here, soft clustering, they just really need to remember it involves fuzzy. Okay, so fuzzy, then it's the probability. Okay, and then the remaining idea, it's very similar, is it? But over here, it involves probability. Okay, so then we also assign the cluster membership for each point, is it? But over here, it involves the probability. Of the other is similar. Okay, so that's regarding the fuzzy one. Okay, fuzzy one. Okay, and then next, let's see. How do we find the optimal number of clusters? Okay, using k-means. So one approach is, we call it arable method. Okay, so basically arable method, it uses the within cluster SSE. Okay, so we also call it distortion. Okay, how can we get to the value? We use the inertia. Okay, and the inertial attribute can get from the k-means model. Okay, so basically the idea is, so the x-axis is number of clusters. So basically it's that k number, is it? And the y-axis is that SSE. Okay, the distortion or inertial, or we say inertial, is it? So based on the relationship, is it, between the SSE and number of clusters. So arable, so it's, so if you try with different number of clusters, is it? Suppose this is 2, 3, 4, 5, something 6, is it? And it's kind of, you can see over here, it's a turning point, is it? And over here, then it's kind of getting stable, the inertia and the distortion, is it? And it's also within like your acceptable sum of the square of error, is it? Then you may say, okay, 3 cluster is the optimal number of clusters in this case. Okay, so it's a graphical tool, the elbow method. Okay, then to help us to estimate the optimal number of clusters. And of course, intuitively, is that if the number of clusters increase, the distortion should decrease. They should decrease. Okay, so that's regarding the elbow method. Another concept we will see is how can we check if our model is good or not? Is it previously, because this is regarding clustering, okay, it's not, it's very hard. You use the accuracy or use the confusion matrix. Is it, it's hard for us to use those. It's ROC, AUC, is it all of those to measure. Okay, so for the clustering, because all of this, you have some reference value, is it, to compare. Okay, because you have the real target value, and then you also have predicted ones, is it? And you compare these two, is it? So we use those performance matrix to measure that makes sense, is it? But over here, it's clustering, is it? So how can we quantify the quality of our clustering, is it? So in this regarding, we have a concept, we use something we call it silhouette plots. Okay, silhouette plots. So silhouette plots is some graphical tool, okay, to plot a measure of how tightly grouped the samples in the clusters. Is it? So if your cluster, the samples in your cluster very tightly grouped, then that means it's a good clustering. Otherwise, it's not good. And generally speaking, they said the silhouette coefficient bounded in the range of -1 to 1. Okay. And also, it's relative bad, or at least suboptimal. Okay. Silhouettes have visibly different lengths and weights. Okay, in our example, we can clearly see what can be stated as a good one and what can be stated as a bad one. So that's regarding clustering. Okay, so let's first stop the concept part about k-means. Okay, so what next? Let's take a look the example, okay, to have better understanding. So the first one we are going to discuss is k-means, okay, clustering. And over here, we are going to use sklearn. And for our data set, in this case, we borrow some data set from sklearn, okay. It's called MakeBlobs, okay, some random numbers. And then we plot of the data set. And you can see, is it? So that's just some random data generated, okay. But they are kind of grouped together, is it? Okay, and then let's see, how do we use k-means? So to use k-means, you need to use sklearn's the cluster package. Okay, then you import this specific module. Okay, so then you just initiate the k-means. But you can see with k-means up front, you need to specify the number of clusters. So then this involves trial. Okay, and error. And there are some parameters. Okay, so this n initial, you can also specify the initial. So use k-means or k++. Here we didn't specify, so the default is k++. Okay, if you don't want to use k++, then you can use the random one. And this n initial parameter is what? Is that it's number of times the k-means will run with different centroid seeds. Okay, with different centroid seeds. So that's regarding that parameter. And the maximum number of iteration is for some single run. Okay, and the tolerance is it, so you can also specify the tolerance, the difference in the clusters, okay, of 2 consecutive iterations. So this is similar as what we saw previously in other learning models, okay, similar concept. So then after that, then we can do predict with our samples. Okay, so this is a predicted values. Basically, it's based on which class. Is it, in this case, we should see 3 cluster. Is it 0, 1, 2? Okay, 3 different cluster. Then we are going to do scatter plotting again. Okay, and here with the scatter plotting, when we pick the data, we use conditional. Okay, Python conditional for our indexing picking. Okay, that is fine. Is it? So the first group should be what? Should be all the first class, first cluster. Okay, cluster 0. Then we pick. Then we get their x1. This is x2 as the first dimension, second dimension values. Okay. Then we give them some color, okay, give them some, and draw it with some marker, okay. And then we also have the label. Then this is the second cluster, that, so cluster 1, second cluster. And the third one, third cluster. So over here you pick because the sample values is within a list, is it? So for the first dimension, is it for which one you are going to pick? Is it we can select using conditional? Is it filtering to select the index? Okay. And then we can also find, so once you do the k-means, you can retrieve the attribute. This is the cluster centers attribute, is it? So you can retrieve this attribute, okay, this attribute for the cluster center, okay. And then what we do is we can clearly see over here it gave different cluster. Is it quite good? Is it the cluster? So already identified for the samples with different cluster and also shows the centroid point. Okay. So that's regarding this k-means. And then next, let's see the elbow method. Okay, how to use elbow method to find the optimal number of clusters. Okay, with the, because right now we don't know how many clusters we need, is it? So the idea is you use a loop, and the loop from 1 over here to 10, is it? And that iteration will take care of number of clusters. And over here, we still use k-means, okay? So similar parameters. Then we call fit, okay? And over here, we have the list of the distortion values, and you get from where? From the inertial attribute, from the k-means, okay? The initial attributes, you get it. Okay, once we have this, then we can do the regular plotting, etc. So with this plotting, then you can clearly see that, so this is the elbow, is it? So over here, you find the elbow point, is it, the turning point. Then after that, it looks like the change is not much. And also over here, you can clearly see the distortion decreased quite a lot, is it? So we can see, okay, optimal number of clusters, there is 3, is it? And if, or you can have more, 4 or 5 or 6, but you can see it doesn't improve your inertial value a lot, is it? So we can say, okay, number of cluster in this case is 3. And then the next concept is about the silhouette plots. Okay, so silhouette is going to be helpful for us to quantify the quality of cluster. Okay, so what is silhouette value? The silhouette value is to measure similar object close to its own cluster, the cohesion, okay, of a sample to its cluster and compared to other cluster. And generally speaking, we already see the silhouette values range from -1 to +1. And the higher, the better, because the higher that means the object will match to its own cluster and poorly matched to neighbor clusters. Okay. And if most objects have high value of silhouette values, then that means the clustering configuration is appropriate. Okay. Otherwise, that's not good. Okay. Otherwise, that just means too many or too few clusters. Okay, so that's the concept part regarding silhouette. It's still kind of hard to understand, okay, just based on that explanation. So let's see. So over here, we are going to, so silhouette, it's also from sklearn's matrix, okay, just like if you recall the accuracy confusion matrix, etc. of those. So over here, we still use k-means, and you still need to specify the number of clusters, is it? Then you can predict, you generate all of the target values for different clusters, okay? And then based on that y, so that y should have 0, 1, and 2, is it, for each of the sample. So the unique, then we have 3 labels. We only should have 3, okay? Okay, then to use a silhouette, you just use the silhouette samples. Then you plug in the sample attributes. This is the clustering group number, is it? And you also need to specify what's the measuring matrix. Okay, and then next we can start to do the plotting, okay? Do the plotting. But before we show the plotting, so first let's take a look at the result. So this is the result, okay? For the result, the x-axis is silhouette coefficient. Silhouette coefficient, generally we say it's between -1 to 1, is it? And the y-axis in this case is the cluster, the first cluster, second cluster, or third cluster, is it? So we have this kind of silhouette plotting, and based on this silhouette plotting, we can see the result is pretty good. Okay, so the clustering is good. Why? Because you can see the silhouette values is not that small, and also all the three shape kind of very similar. Is it not differentiate a lot? Okay, so this is good clustering. Okay, so how this plot is generated? So we have this silhouette samples be generated. Okay, and if you recall over here, when we draw, is it? So this is y, so we have y low and also y upper values. Okay, and both of them you initial as 0, but then because of different clusters, is it? So the value going to change. Okay, so we are going to loop through the 3 different clusters. Okay, 3 different clusters. And how do you get each cluster's silhouette values? Here, then we can collect the silhouette values. Okay, silhouette values is from the silhouette. So this is all samples silhouette values. But then we need to filter out. Filtering out is it based on the clustering group here. Is it C is from the different group? Is it different group? Okay, then we kind of call the soft value to soft it, and then you have this whole cluster. Okay, then this one is one cluster. One cluster. So you can measure how many is it in this cluster. So then that is your upper Y values. Okay, and you can justify the color for this group. Okay, and then we just do bar plotting. Okay, the bar plotting, then this is the width, this is the height. Is it for the bar? Okay, and then you select the respective color. Is it? Okay, and then we also do what? We also try to do the means. And over here, you update the low because then it's going to start your second cluster. The second cluster, the low part is the length of the silhouette of the first group, is it? So that's how you update it. And then we find the mean value. That's how that's red mean line come from. Okay. Okay, then we do this bar plotting. So that's the result. So this is called silhouette plotting. Okay, and it's visual. It's very visualization. Is it? Visualize, we can clearly see this 3 group. Kind of, shape, not too much. Is it? So it can reflect the result is good. Okay. If we take a look, suppose for the same data, then we specify 2 clusters. Okay. With the 2 cluster, then if we just do scatters drawing, it's kind of like this. Is it? And the visualization, we can also see it's not a very good choice. Is it? Then let's see the silhouette. So we apply the same plotting approach to this clustering. Then you can clearly see that the silhouette coefficient for this one, it's far off, further away from one. This one is not bad, is it? And also you can clearly see the shape of this two, is it? Off a lot, is it? So this not a good choice. Clearly we can see, is it, based on this visualization, okay? So that's regarding silhouette, okay? So basically the first concept regarding k-means, we completed in detailed discussion. So Wednesday, we try to finish the other two.